Yeah, welcome everybody. So today we'll solve some questions on engineering mathematics, and it is regarding the daily quiz, which was based on the syllabus of first week of April 2025. Okay, so there are like 4 questions, and we'll solve them primarily based on linear algebra topic. So the first question is they have given you a system of linear equations. So there are 4 unknowns, 4 variables. X1, X2, X3, X4 are the unknown variables, and there is one more unknown, which is beta, which is on the RHS of the last equation, as you can see in the question. So we need to find out which of the following option holds. Okay, so it is first thing that you should remember is this is not a single option correct question, because they are asking you about options. Okay, so it can be a multiple option correct question, and we need to find which is true. Okay, in many questions they ask what is false or something like that, but in this question they are just asking you to find the correct option. Okay, so always pay attention to the question, because many times in a hurry students make a mistake in this kind of thing. Okay, so then there are 4 options. First is number of pivots. So then you should know what is the concept of pivot in the context of system of linear equations. And then option B and C are basically dealing with the value of beta. So that we'll also see, because everything boils down to beta in this question, and this is a typical template of a question that can be asked in your GATE exam also. And lastly, in option D, they are talking about free variables. Okay, so all of these things we have discussed in our regular classes. So if you had attended that, you should be able to solve this question easily. Otherwise, that is also fine. If you have not attended the previous classes, I'll just explain, because this is a very standard question in the context of Ax equal to B system of linear equations. Okay, so there is a non-homogeneous part on the RHS, and the correct answers are B and D. Okay, so as I told you, it's a multiple option correct question. So many a times students make a mistake here, and they will find option B as the correct, and they'll just tick that one and move on. But yeah, you have to be very careful while reading these kind of things. So we'll solve it. So basically, first of all, in this kind of questions, we need to write the given system of equation. We need to write given system of linear equations in this standard form, Ax equal to B. Okay, so where A is nothing but your coefficient matrix, X is your variable matrix, and B is your non-homogeneity matrix, or RHS matrix, you can call it. So if you do this way, so whatever all the coefficients will be in the coefficient matrix A. So it will look something like this. Since there are 4 equations, right? We have 4 equations. So whatever are the coefficients of first equation, they will form the first row of coefficient matrix. So that will be 1, 1, 3, 1. Okay. It will be 1, 1, 3, 1. So this will be a matrix, A matrix, 4 by 4 matrix, because there are 4 unknowns, 4 variables. Similarly, you have to make the note of all these 3 remaining equations. 3, 2, minus 1, minus 1 will be the second row. Fourth row will be 1, 0, 1, minus 2, because there is no x2 here. Okay, so x2 is 0, so that is 1, 0, 1, minus 2. 1, 0, 1, minus 2, and the last row will be 3, 3, 1, 2. 3, 3, 1, 2. Okay, and your x matrix will be the unknown variables, which are x1, x2, x3, x4. Okay, and B matrix is nothing but whatever is on the right hand side of these equations in the same sequence. So that will be 2, minus 1, minus 3, beta. 2, minus 1, minus 3, beta. Okay. And now, since this is a system of equation where RHS is not 0 or a null matrix, here we also get into this concept of augmented matrix. Okay, so we define something called as augmented matrix, and based on the rank of augmented matrix and the coefficient matrix rank, we deduce whether the system will have unique solution, no solution, or infinitely many solutions. The augmented matrix is nothing but whatever your A matrix is there, add one more column which will be your B matrix. Okay, so the augmented matrix will look something like this. Whatever is your A matrix, keep it as it is, just add one more column to it, and that will become your augmented matrix. So the A matrix remains as it is: 1 1 3 1, 3 2 minus 1 minus 1, 1 0 1 minus 2, 3 3 1 2. Okay, and then there will be one more additional column here because of the B matrix, which is a column matrix. That will be 2 minus 1 minus 3 beta. 2 minus 1 minus 3 beta. Okay, so here one unknown is there, which is beta. Okay, so yeah, so now you have to do the row echelon transformation of this augmented matrix, which is also called as row reduction form, or Gauss elimination form, whatever it is. But basically the idea is you have to make this augmented matrix in a upper triangular matrix by doing the row elementary transformations. Okay, there are some 3 row elementary transformations that also we have discussed, and we'll use those here. So the basic idea is whatever is, see, fortunately here the first row and first column element is 1, otherwise you have to divide that also by the same number. So that part is sorted out here. So then what you can do is you can subtract. See, you can do following operations. You can change R2, and how do you change it? You subtract 3R1 from R2, so that the second row first column element of this augmented matrix becomes 0. Similarly, you can do these operations. So you can modify R3 also, just subtract R1 from it, and similarly R4 you have to subtract 3R1 from it. Okay, so 3 row operations, elementary operations we are doing here. So if you do that, what do you get? This augmented matrix will update as follows. Okay, first row doesn't change because we are not doing anything to it, so it will remain as it is. Then if you look at it, these all 3 elements will become 0 because that's what we are doing by doing these transformations. So then other elements you have to change. Okay, so go row by row, that will be helpful. So in that case, 2 minus 3 will be minus 1. Minus 1 minus 9 will be minus 10. This will be minus 1 minus 3 minus 4. Minus 1 minus 6, this will be minus 7. Okay. Similarly, 0 minus 1 will be minus 1 here. And 1 minus 3 will be minus 2. Minus 2 minus 1 is minus 3. Minus 3 minus 2 is minus 5. Okay. And in the last row, we are doing R4 minus 3 R1. So this will also become 0 because 3 minus 3 is 0. 1 minus 9, that is minus 8. 2 minus 3 minus 1. And beta minus 6. So that term remains as it is. Okay, so this is your one of the steps of your augmented matrix row echelon transformation. Okay. Now the next step is, since we want to convert it into an upper triangular matrix, that is our objective. One thing that we can do here is we can make this element 0. Okay. So this element, if we can make it 0, then then we can focus on this last element later on. But let's do that, and the easiest way to do it is you can use this R2 and R3. Okay. Okay, so what we can do is can subtract R2 from R3. Okay. So you can just modify R3 as R3 minus R2. Okay. So that this minus 1 becomes 0. If you do this way, you'll get the next transformation, or the next step will be the first row remains as it is. We are not touching it. So this is 1 1 3 1 2. Okay. And the second row also we are not touching, so that will be 0, minus 1, minus 10, minus 4, minus 7. Okay. 0, minus 1, minus 10, minus 4, minus 7. Okay. Only R3 is changed here. So now if you subtract 0 from 0, that is 0. Second element also becomes 0. And then 2 minus minus 10, so that is 8. Okay. So this is 0, 0, 8. And then this is minus 3 plus 4, so that is 1. Okay. And the last element will be minus 5 plus 7, that is plus 2. Okay. And R4 remains as it is because we are not doing anything to it. So it is 0, 0, minus 8, minus 1, 0, 0, minus 8, minus 1, beta minus 6. Okay. Now the next target should be this element of minus 8, because if we make it 0, then our triangle, our matrix will become upper triangular. That is our end objective. And there is easiest way to do this. And how do you do that? What you do, you modify R4. And how do you modify? Just add R3 to it. Okay. Because if you do this way, then what happens? You can take a note of this, that other rows remain as it is. There is no change to them. Third row also remains as it is because we are not touching it. We are only modifying the last row. This remains 0, 0 because those elements are 0. Minus 8 plus 8 is 0. Minus 1 plus 1 is 0. Beta minus 6 plus 2 is beta minus 4. Okay. So since this is now an upper triangular matrix, this is the end of your transformation. Okay. And then what you do? Now you check. See, the first 4 columns represent your coefficient matrix, right? The whole thing is your augmented matrix. That is what we are doing. But the first 4 columns represent your coefficient matrix. Okay. So now depending on the rank of these things, you have to make a deduction. Okay. So if you look at here, only at your first 4 columns, that gives you the rank of coefficient matrix A. Okay. So from your row reduction form, you can tell that rank of matrix A is 3 because the last row is all zeros. So rank is nothing but number of non-zero rows in a row reduced form or row echelon form. Okay. But if you look at your rank of augmented matrix, it depends on beta, because depends on this beta minus 4 term, right? Because other are non-zero numbers. So if beta minus 4, if beta is equal to 4, then what happens? This beta minus 4 term is 0. The rank of your augmented matrix is 3. But if your beta is not equal to 0, rank of your augmented matrix is 4, because those many non-zero, there are no non-zero rows, so rank is 4. Okay. So therefore, now based on this information, you have to deduce, because rank of A is 3, and if rank of A augmented matrix is also 3, so in that case you will have this system will have a solution. Okay. So solution exists. Here, since this is not equal to rank of your coefficient matrix, this is called as inconsistent system, and there will be no solution. Okay. So now you have to go back to your slides options, and you have to check. So what they are saying, if beta is not equal to 0, no solution exists. That is correct. So therefore option B is correct. They're asking if beta is equal to 4, unique solution exists. Okay. So now there is a next question. See, if the ranks are same, then we can just say that solution exists. But since this rank of A as well as rank of, let's say, your augmented matrix AB is less than 4, which is number of unknowns. Okay. So this is the case of infinite solutions. Okay, because you will have one solution, one variable always free in this case. So therefore this is the case of infinite solutions, and therefore there is no unique solution. Okay, so therefore this option option number 4, C, is incorrect because it's a infinite solution. Okay, if it is an infinite, then it is correct. And now number of free variables, as you can see, number of variables, first of all, it depends. See, if beta is not equal to 4, then you cannot say anything because it's an inconsistent system. But let's say if beta is equal to 4, then number of unknown variables is nothing but typical formula is number of unknown variables is nothing but n minus rank of your matrix A or anything, because usually A and AB will be same, augmented matrix, etc. Number of unknowns are 3. This. Okay, but here I would like to tell you that they should have mentioned that number of free variables if beta equal to 4. Okay, because if beta is not equal to 4, then there is no solution. Okay, so the option D should be slightly modified. And option number A says number of pivots. Okay, so number of pivots basically means number of pivots is nothing but number of first non-zero element in row echelon form. Okay, row echelon form. Okay, so if you look at the reduced form your matrix, so you can see there is 1, 2, 3. Okay, so there are 3 pivots here, not 4, because this last element is 0, so you can't consider it as 4. So there are 3 pivots. So this is equal to 3. Okay, but in the option that you see, they are saying number of pivots as 2. So therefore this is also incorrect. Okay, so option B and D are correct in this question, but for D they should mention that beta is equal to 4. Okay, then only option D can be considered, but I think there is a slight information mismatch there. Okay, so then the same question, next question is similar to the first one. Here again you have to do the row echelon transformation for this 4 by 3 matrix. There are 4 rows, 3 columns, 3 rows, 4 columns, 3 by 4 matrix. And then they are saying rank of A is 2, so that means rank of A is 2. So that means one of the row will be 0. All, it has to be all zeros. Okay, so you have to do the same thing here. It is like the sub case of the previous problem. Okay, so we'll do that. But here you should understand it's the same process. Okay, so there is nothing new here. So what you can do is, you have this matrix A, which is 1, 1, 1, 1, 3 by 4 matrix, 1, 2, minus 1 lambda, 5, 7, 1 lambda square. Okay, this is the matrix. And yeah, then what you can do, you can first reduce these column elements. So what you do is you subtract R1 from R2. Similarly, from R3 you subtract 5 R1. Okay, so that the first column elements become 0, 0. And then first row remains unchanged. There is nothing changing there. And then you have 2 minus 1, 1. This will be minus 2. This will be lambda minus 1. And here it will be 7 minus 5, 2. 1 minus 5 minus 4. And this will be lambda square minus 5. Then what you can do, maybe I'll do it here itself so that the space will be reduced. Now your objective is to make this element 0 because we want it to be an upper triangular matrix. So you can do one simple transformation that you can subtract 2 R2 from it. Okay, and if you do that, what do you get is basically first row remains as it is. There is no change to that. 1, 1, 1, all ones. Second row also remains as it is because we are not touching it. This will become lambda minus 1. Whereas the last row, this is 0 minus 0, 2 minus 2 is 0, minus 4 plus 4 is 0, and this will be lambda square minus 5 is already there. And then you are subtracting 2 R2. So basically you are subtracting 2 lambda plus 2. Okay. this will be the final thing. So I'll just mention this last term because that is of our interest. So this term is nothing but lambda square minus 2 lambda minus 3. Okay, so this is your last element of the last row, third row, fourth column. Okay, so now what they are saying is rank of this matrix is 2. Okay, so rank of this matrix is 2. This is your A matrix, right? So for that to happen, this has to be equal to 0, right? Then only you will have the third row which will be all zeros. Okay, so in that case, then the question becomes simpler because now you have to find the values of lambda for which this lambda square minus 2 lambda minus 3, which is your last element, becomes 0. And you can do that because this is nothing but, lambda minus 3 plus 1. Okay, therefore you have values of lambda as 3 or lambda is minus 1. So for both lambda values, the last element will become 0. So now you go back and check your options. So if you look at the options, correct option is minus 1 and plus 3, right? So that is minus 1 and plus 3. So minus 1 and plus 3. So this option B. Yeah, so answer is option B. That is what we also got. Okay. So this is actually, you can consider it as some case of first problem. Okay. Because in first problem, they had asked you the next part of it also, which is considered, concerned about the system of linear equations and how do we deduce the number of solutions or nature of solutions for that. Okay, so then let's move on to the third quiz question. So here you have to pay attention to one thing. They're asking you which is not true here. Okay, they are not asking you what is true, which is not true. So basically, what is false. So if you look at options in this question, it is not clear. But since they are saying only one option, so that means 3 will be true, 1 will be false. Okay. So if you look at the first option, they have given you lambdas as the n distinct eigenvalues of a n by n square matrix A. Then their corresponding eigenvectors are linearly independent. Okay, this is true because I should just write this is true statement because it's a standard property, standard result, you can say. I mean, we discussed a lot of properties of eigenvalues as well as eigenvectors in our regular classes. And this is the first thing that we discuss because it has a lot of implications. Okay, diagonalization, etc., etc. So first is true, so that is not our answer. The second option is if A is an invertible matrix with eigenvectors V corresponding to eigenvalue A. Okay, it should be actually lambda here because A is a matrix. There is a typo that there, so ignore that. Then V is an eigenvector of A inverse corresponding to eigenvalue 1 by lambda. This is also true. This is also property of these eigenvectors and eigenvalues, and there is a simple proof for it because let's say for matrix A, lambda is the eigenvalue, and corresponding to lambda eigenvalue, eigenvector is V. So what you can do is you can pre-multiply by A inverse on both the sides here. Okay. Okay. So then what happens? This is A inverse A lambda equal to A inverse, A inverse, right? Not lambda inverse. A inverse V lambda. Okay. So A inverse into A is I, and if you sorry, this is A into V, not lambda, because this is matrix, right? Yeah, that is correct now. And just for the sake of better representation, I should write it as lambda V because this is a standard notation used in every book. So this becomes V equal to A inverse into lambda into V. So the eigenvalue is actually a scalar. So what you can do, you can take it on the other side. So this becomes A inverse V equal to 1 by lambda into V. Okay. So therefore, if you compare this with equation 1 and equation 2, so for A inverse, the eigenvector remains the same, whereas the eigenvalue scales by 1 by lambda. Okay. So this is the standard result, and that is what it is mentioned. So for inverse of given matrix, the eigenvalue becomes 1 by lambda, whereas eigenvector corresponding to that original lambda remains the same for both A and A inverse. Okay. Now option C and D are more or less talking about something called as positive semi-definite matrix. And the important property that you should know about positive semi-definite matrix to solve this question is the nature of the eigenvalues for positive semi-definite matrix. We usually use PSD as the acronym for such matrices. Okay. So the property of such matrix A, which is if A is a positive semi-definite matrix, its property, there is a standard property which says that all lambdas, all eigenvalues of this matrix will be greater than or equal to 0. There is one more case where you have matrix A as positive definite matrix. In that case, all eigenvalues will be greater than 0, not equal. But here, since it's positive semi-definite, there is a possibility that one or multiple eigenvalues could be equal to 0. Okay. But what they are saying is, they are not asking you about the eigenvalues of A. They are asking you something else. They are saying if A is PSD and epsilon is some positive real number, then A plus epsilon I may have been 0 eigenvalues. This is not correct because it will always have positive or definite. Yeah, this is not true, because what happens, see, A may have lambdas greater than or equal to 0, but when you add a positive epsilon and then I is identity matrix, that shifts all the eigenvalues by epsilon amount. Okay, so what I'm trying to tell you here is, in such case, if you do A plus epsilon I transformation where this epsilon is greater than 0, which is mentioned in the question, so that means all lambdas of A are shifted by epsilon. Okay, because you'll see the next question, it is actually the same question as this, but there you have some function of your given matrix A. Here it is also some function of your given matrix A. We'll see that in the next slide or next question. Okay, so if all the eigenvalues are shifted by some positive distance, that means all lambdas are greater than 0 for this new matrix A plus epsilon I. Okay, so therefore option C is incorrect. But option D, if you see, they are saying A plus epsilon I is always positive definite matrix. That is true, because as I told you, all the eigenvalues are greater than 0. That means, therefore, this A plus epsilon I, which is a updated or new modified matrix, that will be is a positive definite matrix. Okay, because now all the eigenvalues are greater than 0. Okay, this is also called as PD matrix. Okay, so therefore, the correct answer is, oh, sorry, I clicked somewhere else. Yeah, so therefore, the correct answer is, oh, sorry, this is true. So the answer should be option C, because they're asking you the false statement. So answer is false C. Answer is option C. Okay, so like that. And the next question is actually the extension of this question, because there is a standard result here, because this is a typical question that is asked. So I'll just mention you. This I discussed in the regular classes also. Okay, so if lambda is an eigenvalue of, let's say, matrix M here, okay, then if you define some function of matrix M, okay, this f of M is any matrix function, okay, then, oh, actually here it should be and, because then will come. Then f of lambda is an eigenvalue of your matrix function f of M. Okay, this is a standard result. And why do we use that? Because see, you have some matrix M and they have defined some matrix function, okay, M cube minus M. So it's like a polynomial matrix function. And they have given you lambdas of your original matrix M, and they're asking you to find the eigenvalue of the matrix A, which is some matrix function of M, but the highest magnitude. Okay, so first you should understand that, if you are deriving some matrix function, polynomial matrix function in this case, then in such cases, whatever is the eigenvalue of original matrix M, by same function you have to transform that to get the eigenvalue of that matrix function. Okay. So what do I mean by that? Is basically, let's consider one eigenvalue. So for lambda equal to 2, which is one of the eigenvalues of matrix M, then corresponding eigenvalue of matrix A is nothing but you have to apply same function. So that will be lambda cube minus, see this f of M here, this f of lambda in this question will be lambda cube minus lambda square plus 6 lambda. Okay, so depending on whatever is your lambda, just put that. So here lambda is 2, so that will be 2 cube minus it is lambda square plus 6 lambda, right? So lambda square plus 6 lambda. Okay, so that is 8 minus 4, 4 plus 12, 16. Okay. Similarly, for lambda equal to 5, corresponding eigenvalue will be, for matrix A will be 5 cube minus 5 square plus 6 into 5. Okay, so that is 125 minus 2500 plus 30 is 130. Okay. Similarly, for lambda equal to 9, that will be 9 cube minus 9 square plus 6 into 9. Okay, so that is, you can do this calculation, it turns out to be 702 because 729 minus 81 plus 54. Okay, so this 16, 130 and 702, these are eigenvalues of your matrix A. Okay, and they're asking the highest magnitude. So magnitude wise they're asking, so this is the highest magnitude eigenvalue. Okay. And yeah, that is the same answer, that is the correct answer. Okay, so like that. So for these type of questions you should remember this property of eigenvalues and matrix function of given matrix. Okay, so I think this is the last question. Yeah. Okay, so with this I'll stop and maybe see you in the next week's quiz solutions. Okay, bye.